Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH of a buffer solution that contains an acid and also a salt containing the conjugate base of that acid after a strong base has been added. The specific problem you're asked to solve asks you what is the pH of a 0.25 liter buffer solution that is 0.30 molar ascorbic acid and 0.25 molar potassium ascorbate after 0.050 moles of sodium hydroxide have been added. In this case, there's a strong base, sodium hydroxide, being added. When a strong base is added to a weak acid solution, which is what ascorbic acid and potassium ascorbate is, then a neutralization reaction occurs. In this case, ascorbic acid is neutralized by the hydroxide ion that comes from the addition of sodium hydroxide. So when sodium hydroxide is added, it's a strong base and it pretty much completely dissociates into sodium ions and hydroxide ions. So it's this hydroxide ion that does the neutralizing of ascorbic acid. And this happens according to the following equation. You have ascorbic acid plus the hydroxide ion going to water, which is what results when ascorbic acid donates a proton to the hydroxide ion, and the ascorbate anion, C6H7O6 minus. So this is what's left over after ascorbic acid has given up a proton. Notice here that there is a one-way arrow pointing from left to right rather than a regular two-way arrow designating chemical equilibrium. And that's because when neutralization reactions involve a strong base such as sodium hydroxide, they essentially go to 100% completion. So almost no reactant is reformed in this neutralization reaction. So to solve this type of problem, you have to set up a table, but it's not an ice table. It's a different kind of table. And you have 3 rows to this table. You have a before row, you have a change row, and you have an after row. So all of these refer to the neutralization reaction. So you're not dealing in molarity either for the units of the different species present. Now you want to know the number of moles of each before the neutralization reaction occurs, the number of moles of each and how that will change during the neutralization reaction, and how many moles of each will be left after the neutralization reaction. So what you need to do then to fill in the first row is know the number of moles present initially, or the number of moles of each of those species that are present before the neutralization reaction occurs. So the first thing you can find is moles of ascorbic acid. And you can figure this out because you're given the volume of that buffer solution, and you're also given the molarity of ascorbic acid, which is 0.3 molar or 0.3 moles of ascorbic acid per liter. So liters will cancel out, and when you do the math, you have 0.075 moles of ascorbic acid. So you can fill this number in for ascorbic acid for that first row in your table. You have 0.075 moles of ascorbic acid present before the neutralization reaction occurs. As far as moles of hydroxide, you're given this in the problem. You're told that 0.050 moles of sodium hydroxide are added, and because the reaction stoichiometry is 1 mole of sodium hydroxide to 1 mole of hydroxide, if you have 0.050 moles of sodium hydroxide, you also have 0.050 moles of hydroxide. So that is also what's present initially. And then the other species of interest is the ascorbate anion. So you do the same thing as you did for ascorbic acid to find the moles of ascorbate anion. You take your volume and you multiply it by the molarity of potassium ascorbate, and you have 0.25 moles of ascorbate ion per liter. And again, because when potassium ascorbate dissociates in solution, so we'll write it up here, potassium ascorbate dissociates into potassium plus the ascorbate anion, and the molar ratio between that ascorbate anion and potassium ascorbate is 1:1 according to the reaction stoichiometry, then if you have 0.25 molar potassium ascorbate, you also have 0.25 molar ascorbate anion. So that's why you can use this 0.25 moles per liter to find the number of moles of ascorbate anion. So when you do the math here, you find that initially you have 0.625 moles of ascorbate anion. So you can put that in your table under the ascorbate anion. For the change row, all you're going to do is subtract the moles of hydroxide that is present initially, because for every mole of hydroxide added, you're going to lose 1 mole of ascorbic acid and you're going to gain 1 mole of ascorbate anion. So for however many moles of hydroxide are added, you have a 1:1:1 ratio. So you're going to subtract 0.050 moles from both of the reactants, and you're going to add 0.050 moles to the products. You're going to be losing the reactants and gaining the products. And then all you have to do is do the math. So you subtract 0.050 from 0.075 and you'll get 0.0250, and then when you add 0.05 to the moles of ascorbate anion, you get 0.1125. So now you have the number of moles of each of the species present after the neutralization reaction is complete. So what we're trying to do for this problem, if you go back to the question, is to find the pH. And to do this, you can find the hydronium ion concentration using the Ka for ascorbic acid. And in order to do that, we need to know the concentration of ascorbic acid and the concentration of ascorbate anion. So assuming that the solution volume remains the same after the addition of NaOH, so we have this solution volume of 0.250 liters, assuming that adding the sodium hydroxide does not change that number, we can easily find the concentration of ascorbic acid and ascorbate anion by dividing the moles by the liters of solution. So the concentration of ascorbic acid will be 0.025 moles, which again is what is left over after the neutralization reaction, and you're going to divide that by the total volume of the solution that you're given to be 0.250 liters. When you do the math, you get 0.1 molar for the concentration of ascorbic acid, and then you can get the concentration of the ascorbate anion in a similar way. You have 0.1125 moles of ascorbate anion, and you know this because you calculated it in your table. You have the same volume, so you have 0.250 liters, and when you do the math, you get 0.45 molar for your concentration of ascorbate anion. So in order to use the Ka value, you need to know the principal proton transfer reaction that's occurring in solution after the neutralization reaction is complete. So after all of that sodium hydroxide addition is complete. So when that is all finished, what you're left with is the ascorbic acid transferring a proton to water to give you the hydronium cation plus the ascorbate anion. And this reaction is in equilibrium. So the reverse reaction is also occurring. And the equilibrium constant for this reaction is known. It's the acid dissociation constant for ascorbic acid. And you can look this up in a table of acid dissociation constant. So we're using the Ka value for 25 degrees Celsius, assuming this is occurring at 25 degrees Celsius. So the equilibrium equation is Ka is equal to the hydronium ion concentration multiplied by the ascorbate ion concentration divided by the ascorbic acid concentration. Now we want to solve for the hydronium ion concentration, and we know all of the other concentrations, so you want to rearrange this equation to solve for the hydronium ion concentration. So you'll get hydronium ion concentration is equal to Ka times the ascorbic acid concentration divided by the ascorbate anion concentration. And you know both of those concentrations and the Ka value. So all you need to do is substitute those values in here. So Ka is equal to 8.0 times 10 to the negative 5. You've determined your ascorbic acid concentration to be 0.1 molar, and you're going to divide that all by the ascorbate anion concentration, which you've determined to be 0.45 molar. And when you do the math, you find that the hydronium ion concentration is 1.8 times 10 to the negative 5. And you're almost there. So you have your hydronium ion concentration. The last thing you need to do is find the pH using that. And very simply, you know that pH is equal to the negative log of the hydronium ion concentration. So if you substitute in this number for the hydronium ion concentration, you'll find that you get a pH of 4.75. So that's your pH, and you're done.